Welcome back to AI Talks with Chris and Nita. Ready for a deep dive into something pretty mind-blowing?
I am. Quantum machine learning. It's where science fiction starts to look a lot like reality.
I was going to say, it sounds a little out there. But we're talking about seriously powerful stuff, right? Not just faster computers, but like a whole new way of doing computing.
Right, exactly. It's using quantum physics, the laws of the universe at the tiniest level, to do computing in a way we just couldn't before.
Okay, I'm already intrigued. So quantum machine learning, QML, what's the elevator pitch?
Okay, so imagine combining the almost magical world of quantum mechanics with the data crunching power of machine learning.
Okay, I'm with you so far.
It's like having this universal decoder room to understand, to analyze some of the most complex data you can imagine.
All right, before we go any further, can we back up a sec? Everyone's talking about quantum computers these days. What makes them so different from the computers we use every day?
It comes down to the building blocks. Your laptop uses bits, right? Like a tiny switch, on or off, 1 or 0. But a quantum computer, it uses qubits.
Qubits, okay.
Think of a qubit like a spinning coin. It can be heads, tails, but it can also be spinning, so it's both at the same time. That's superposition.
Wait, both at the same time? That's not just faster, that's like a whole other level?
Yeah. That's the crazy processing power we're talking about. Think of this. A system with just 300 qubits can hold more possible combinations of information than there are atoms in the entire universe.
That's just wow. Okay, so back to quantum machine learning. How does it use that power? Can I just plug my spreadsheet into a quantum computer and get amazing insights?
Not quite. Think of QML as a translator between the language of, our everyday data and the language of the quantum world.
Interesting.
It allows quantum algorithms to really dive deep into massive data sets, spot these super intricate patterns that would be completely invisible to even the most powerful classical computers.
So we're not just crunching numbers faster, we're uncovering hidden connections that were always there.
You got it. And that's what's so exciting. It opens up this whole new world of understanding complex systems that were just out of reach before.
I'm starting to get it. So what are the tools? What are people using to actually build these quantum algorithms?
Well, one of the key players is something called TensorFlow Quantum, or TFQ.
TensorFlow Quantum, okay.
It gives researchers the tools to create models that can decode those hidden correlations in quantum data.
So it's like a quantum coding language.
Yeah, kind of. It allows researchers to talk to these quantum computers, develop new algorithms, really push the boundaries of what's possible.
Gotcha. Okay, so we've got quantum data, the tools. But how do these quantum computers actually process the information? It's different from our regular computers, right?
Totally different. Classical computers work step by step, but quantum computers, they use quantum logic gates, and these gates work on qubits that are entangled, meaning they can manipulate data in tons of ways, all at the same time.
Okay, so while a classical computer is slowly working through a calculation, the quantum computer is doing this massive parallel processing dance.
Exactly. And that ability to explore all those possibilities at once is what makes quantum computers so powerful. They can tackle problems that would take a regular computer years, decades, maybe even millennia to solve.
I'm on board with this quantum speed train.
Yeah.
But can we get to the real world stuff? Where will QML actually make a difference?
Oh, lots of places. One area is deep learning that relies on these huge matrix multiplications.
Sounds intense.
It is for a classical computer, but quantum computers can do those calculations super fast. So suddenly you've got neural networks that are way more powerful, way more efficient.
So we're not just training them faster, we're opening up possibilities that were just impossible before.
Right, and that means more accurate medical diagnoses, developing new materials with properties we haven't even thought of, all sorts of amazing stuff.
This is just the tip of the iceberg, isn't it?
Oh yeah. QML is also a potential game changer for drug and medical device design. The calculations needed to understand how atoms work in molecules. It's super hard for classical computers, but perfect for quantum computers.
So we're not just crunching numbers, we're simulating the very building blocks of matter.
Exactly. It's like having a molecular architect that can test endless designs, find new drugs and therapies way faster.
This is getting more fascinating by the minute. Are there other places where this teamwork between quantum and classical is happening?
Absolutely. We're seeing hybrid computing, where small-scale quantum computers work alongside powerful classical computers to analyze enormous data sets. It's like each one brings their best skills to the table.
A real partnership.
Yeah.
What else are we seeing this teamwork in?
Cybersecurity, for one. The way quantum mechanics works, it has this inherent uncertainty that we can actually use to create super secure encryption keys.
So we're talking about data protected by the laws of physics.
Pretty much. It's really showing how QML can not only improve what we have, but completely change what's possible.
Okay, so before we go any further, it's important to remember that these quantum computers aren't just like souped up versions of our current computers. They work on totally different principles, right?
Right. It's not just a speed boost. It's like a whole new paradigm. Think of it like a candle and a light bulb. Both give you light, but how they work is totally different.
Great analogy. So we're not talking about small improvements, but a potential revolution in how we think about computing.
It really is. And it's such an exciting time to be working in this field. We're really just at the very beginning of what's possible with quantum machine learning.
And I bet our listeners are starting to feel that excitement too. But let's dig a bit deeper into what makes these quantum computers tick.
Sounds like a plan. We can explore how these machines work and dive into the world of quantum algorithms.
I'm ready to go down the quantum rabbit hole.
Ready to go behind the scenes.
Absolutely. We've been talking about quantum computers, but like, what's actually going on in there? How do they do these amazing things?
Yeah.
It's not magic, although it might seem like it. The heart of a quantum computer is those qubits, right? But they're not just like an idea, they're real physical things.
Whoa, okay.
Scientists are using lasers to trap individual atoms, or they're manipulating electricity in these super cooled circuits. It's wild.
So they're creating this environment where those quantum laws can work without interference from, our normal world.
Exactly. And those qubits, they're super sensitive to any disturbance. That's one of the big challenges, keeping them stable and controlled. It's a huge feat of engineering.
I can imagine. So we've got these carefully controlled qubits. What's next? How do we make them compute?
Quantum gates. Think of them as instructions, operations that let us change the state of the qubits. Like logic gates in a regular computer, but, working with quantum mechanics.
So instead of just flipping a bit from 0 to 1, we're doing something much more complex.
Way more complex. Quantum gates can use superposition and entanglement to do things that have no equivalent in classical computing. And we string these gates together to create quantum algorithms.
So it's like a delicate dance, using quantum mechanics, but also controlling it precisely.
It is. That's where the skill of quantum programming comes in. You need to understand both quantum mechanics and computer science.
Wow, okay, so these quantum algorithms, what are they good at? We talked about drug design, deep learning, but what makes them so powerful?
They're great at optimization problems, finding the absolute best solution out of tons of possibilities.
Can you give an example?
Imagine you're a delivery company, and you need to find the most efficient route through a city with, thousands of different roads and traffic patterns and delivery windows.
That sounds like my online shopping nightmare.
Right. A classical computer might have to try every single route combination, which would take forever. But a quantum algorithm could use superposition to explore many routes at the same time, finding the best one much, much faster.
So it's like a superpowered GPS for complex problems.
Exactly. And that's just one application. It could be used for everything from finance to traffic management to designing new materials.
Okay, that makes sense. Are there other types of problems that quantum algorithms are good for?
Simulation is another one. Classical computers really struggle to simulate complex quantum systems, like how molecules interact or how electrons behave in a new material.
Because they're trying to simulate quantum stuff with classical rules.
Right. It's like trying to fit a square peg in a round hole. But a quantum computer, because it already works with quantum mechanics, can simulate those systems really accurately and efficiently.
So it's not just about getting the right answer, it's about understanding the underlying processes too.
Exactly. And that opens up so many possibilities for science and technology.
I'm starting to see the appeal of having these quantum tools. But are there any limitations? Things quantum computers just aren't good at?
Good question. Quantum computers aren't going to replace classical computers completely. They're more like specialized tools.
So they're not going to replace my laptop anytime soon.
Probably not for things like browsing the internet or sending emails. Classical computers are great at those tasks.
It's about choosing the right tool for the job then.
Exactly. And even in areas where quantum computers are better, like simulation or optimization, there's still a lot of work to do. We need to figure out how to translate those theoretical capabilities into real-world applications.
So it's not just about building the hardware. It's about developing the software and algorithms and really understanding how to use these machines effectively.
Exactly, and that's what makes it so exciting. We're still just starting to explore the potential of quantum computing, but the possibilities are truly mind-blowing.
Well, I'm even more convinced that quantum computing is something to watch closely.
I agree. It's a journey with lots of challenges, but the rewards for science, for technology, for humanity, they're immense.
Speaking of rewards, we've talked about the good stuff, but are there downsides? Risks?
That's important. Like any powerful technology, quantum computing comes with challenges. We need to be aware of those.
So let's not get too carried away. What are some of the concerns that experts are talking about?
One of the big ones is cryptography. We talked about how quantum computers could break the encryption that protects our online data. Everything from financial transactions to government communications.
So it's a double-edged sword. The same power that could revolutionize medicine could also undermine our digital security.
Right. But the good news is that researchers are already working on quantum-resistant encryption. It's a race against time, but it's a race we need to win.
A cybersecurity chess match with really high stakes.
You could say that. But cryptography isn't the only concern. There are bigger societal implications too.
Like what?
As quantum computers get more powerful and easier to access, we need to think about who gets to use them and for what purposes. We need to make sure it benefits everyone, not just a select few.
So it's not just about the technology itself, but about building a future where it's used ethically and responsibly.
Exactly. We need to start having these conversations now to make sure that the quantum revolution leads to a better future for everyone. We need to shape the future we want, not let it be shaped by our current limitations.
I love that perspective. So, a healthy dose of caution alongside the excitement. But before we wrap up, I'm curious about your thoughts on the long-term future of this field.
Ooh, that's a tough one. Predicting the future is tricky, especially with something as fast-moving as quantum computing. But I think it's safe to say we're just at the beginning of an incredible journey.
Okay, no crystal ball needed. What are you most excited about for the future?
One thing is fault-tolerant quantum computers. Right now, qubits are really fragile. They're prone to errors.
Right, because they're so sensitive.
Yeah, but if we can build quantum computers that can correct those errors, that would be huge.
You'd be like giving them an immune system, right?
Yeah.
Helping them withstand those glitches.
Exactly. Fault-tolerant quantum computers would be a major step forward. And another thing I'm excited about is new quantum algorithms.
So it's not just the hardware, it's also about finding new ways to use it, right?
Yes, there's a whole world of possibilities out there, and I think we're going to see amazing breakthroughs in the coming years.
Well, after this deep dive, I'm even more convinced that quantum computing has the power to change our world in huge ways. Any last thoughts for our listeners?
Just stay curious. Quantum computing is a fascinating field, and it's changing so rapidly. Keep exploring, keep asking questions, and don't be afraid to dive into the weird and wonderful world of quantum mechanics.
I love that. And to our listeners, thanks for joining us on this adventure into the future of computing. Until next time, keep exploring. It feels like